Hi everyone, my name is Dongwook Go. I'm one of the junior scientists in the EU-funded Orbital Electronics project. This is a project in which we try to understand fundamental aspects of orbital angular momentum of electrons, especially its transport effects. And another goal of this project is to utilize this orbital current for device applications. If you want to know more about the project, please visit our webpage, orbital-electronics.eu. And the main purpose of this video is to give tutorials on this new emerging field, which is quite rapidly evolving, in my opinion. So therefore, I think this is going to be very useful for students who are just entering this field or anyone from different fields of research to understand what's going on in this field and what this field is about. The main aspect of this tutorial is that I will not go through all details and explain in a very logical and thorough manner. Instead, I have chosen to explain several very core physics concepts that are very important to understand many, many different effects, so that once you understand that, you should be able to follow all other literatures on your own and also construct physics concepts and more detailed concepts on your own. So please understand it as a more sketch, but sketch that contains quite important pieces. This is the first part of the tutorial, part one, uh, where I'm going to explain you what we mean by the orbital information of black electrons. And, and I'm going to explain you what the orbital texture is. In the second part, we focus on electric response of the orbital angular momentum and how angular momentum is induced by electric field in effect called orbital Einstein effect, and also how angular momentum can flow as a current. And this is described by orbital Hall effect. In the third part, this is more relevant in the application to spintronic side, and this is about interaction between orbital angular momentum and magnetization. So I will explain you how orbital angular momentum can excite magnetization dynamics by exerting torque called orbital torque, and how the magnetization dynamics can result in orbital angular momentum in non-equilibrium. So torque and pumping are reciprocal effects each other. So the first part, let's begin the first part on the degree of freedom of orbital. To start with, um, let's try to understand what this field is about. And Orbitronics, in a way, shares a lot of many features with spintronics. For example, in spintronics, we try to utilize the intrinsic spin degree of freedom of electron because spin is an intrinsic property of a fundamental particle. Like mass, electron comes with mass, charge, and spin. And these three are complete. They can completely describe electron particle even in free space. So, so it's quite intuitive in spintronics in the sense that you can think about, I always say, flying arrows. So you have spin up and down arrows moving in all different directions. But when these arrows are moving in the same direction, with the same ratio of spin up and down, we call this pure charge current. And on the other hand, when spin up and spin down, electrons are moving in the opposite directions. We call this a pure spin current because it doesn't involve any charge current. So the interplay between charge current and spin current is really an essence of spintronics, which is quite beautiful. Orbitronics shares a similar idea in the sense that we replace spin by orbital. And in a solid state, it solid is consisting of many different atoms, and atoms have attributes called atomic orbitals. And there are many different orbitals like s, p, d, f orbitals. So we can think of utilizing this information. The first thing that is a bit unclear is that actually where this information is coming from, because this is not really a fundamental property of a free particle, but rather a derived property of an atom. So I will come to this point very soon later. And the second thing that is a bit unclear is how we can move this information, like spin current. So can we move this orbital, which is actually a local quantity attached to an atom? But is it possible? Yes, this part will be covered in the second part of the tutorial. that actually orbital polarized electrons can move to the right or to the left, depending on the perturbation that we apply. And this transfer of angular momentum can take place by electron hoppings. But first, let's try to understand what this degree of freedom is. So we are talking about electrons in a solid. Electrons in a solid is different from electrons in a free space that is a Dirac particle. And electrons in a solid state is called a Bloch state. And Bloch state is a product of a plane wave and a periodic part. And this periodic part has, in fact, a very, very important information of Bloch function, where on how which atom this is derived and which orbital it is derived and which spin it contains. So if you look at the Bloch function in detail, the first thing that you see is a very slow modulation in Beloff function of plane wave modulation, but you also see quite rapid variation of wave function. And especially near atomic center, this Bloch function actually resembles so much of that of atomic orbitals. So that's where atomic orbital enters in the Bloch function. And so therefore, it's quite natural to think of constructing a Bloch state from atomic orbitals. And to do that, we can have linear combination of atomic orbitals phi m at different sites at large r, and large r is a Bravais lattice. And sometimes this phi m is called Wannier functions, by the way. So anyway, by attaching a plane wave factor of this exponential I k dot r, one can show that this calligraphic phi is a Bloch function that is invariant under a discrete translation. So one can easily show that by translating this function by large R, you can actually replace the variable in the definition of Bloch function like shown in this way. Please check on your own. And at the end, what we find is that we get the eigenvalue of the translation operator by large R. So indeed, this state is invariant or discrete translation, meaning it's a good state for describing electrons in a periodic solid. So we can think of this phi m as a basis state. And therefore, a general Bloch state can be expanded in terms of this phi m. And for example, phi m can originate from s orbital, px, or py orbitals, and there can be different coefficients on each. And these coefficients generally depend on k. And by the way, this coefficient Cmn is called n character of the n spanned. So the weight of this coefficient, by this we call it, okay, this band has 50% s character or 20% px character, like that. So this is one terminology that you must learn, and you will encounter a lot in many papers. Another very important feature that I want to really emphasize is that the c is a function of k in the momentum space. It's not a constant. So therefore, c changes in k space. So therefore, orbital character changes smoothly in the momentum space generally. And this is called orbital texture. So the question is then, what determines this orbital character? Of course, where the band is coming from. And the second, how orbital texture appears. And orbital texture generally appears from orbital hybridizations. So let's first look at px band, py band, and let's assume that they do not interact each other. So they are px Bloch function, py Bloch function are the eigenstates of the Hamiltonian in this case. So the band orbital character looks like this: px character, py character. That's it. It's so simple and somehow boring. But then now I'll let these two bands interact each other and hybridize. So if you overlap py, this contour with px contour, what you see is that this clover shape. And in the intermediate region where two bands meet, you see that the orbital wave function will smoothly vary. So The first band that you see in the outer circle is radial type of texture. We simply call this radial quite often in the paper. And the other one in the inner circle has a tangential arrangement of orbital character. So we call this a radial texture of a band. So as you can see, the orbital texture is a very natural consequence of orbital hybridizations. And so therefore, because hybridizations are very natural for different orbital wave functions, once you put them together, they will start to hybridize in all possible ways. So therefore, orbital texture is also ubiquitous in many multi-orbital systems. And orbital textures come in many different shapes and many types. Even in centrosymmetric systems, there can be radial tangential types, terrestrial house types, or can also appear in T2G, d orbital system, or EG orbital systems, as studied in the following paper by Han, 2023. And one might wonder what really determines the shape of orbital textures. And this is a quite actually complicated material property, unfortunately. So it depends a lot on delicate on orbital occupancy and hybridization and how large orbitals are. But there is a very important constraint on this, that is symmetry, because symmetry constraints what type of hybridizations are allowed or forbidden. So I'm going to come to this point slightly later. But anyway, although there can be many different type of textures, there is a one model that you can solve and you can really understand into the very bottom of it to understand what orbital textures are and what type of properties that you would expect. And this model is called orbital texture. And this appears first in the description of orbital Hall effect in silicon by Bernavik et al. 2005. And about 13 years later, I and my PhD supervisor studied this model to understand the microscopic origin of orbital Hall effect. The orbital texture model has two terms. First, kinetic energy, which is constant, so it's quite boring. And the second, rather interesting kinetic energy, which is quadratic in K, but K depending on the projection to L. One important point is that this Hamiltonian has very, very high symmetry. It means that the Hamiltonian is invariant under time reversal, inversion, mirror, rotations. Therefore, you would expect that this is a low energy realization of many, many different materials. And solving this Hamiltonian is quite easy. For a p-orbital system, for example, you can have matrix representation of L in the following way, and you simply diagonalize the Hamiltonian. And this is actually a good exercise of quantum mechanics, angular momentum algebra especially. So by looking at the quantum number m in the quantization axis along K, you see that m equals 0 state has a radial texture. And a radial state looks like this. So we have a kind of px-like state in the direction of K, I'm sorry, pz-like state along the K, and the functional form of the radial state has cosine and sine dependence on the px block function, py block function. For m equals plus minus 1 state, they are degenerate, doubly degenerate, so therefore we can have any choices, as any linear combinations are possible. So one of them is a tangential state, which is orthogonal to the radial state, has this dependence. So it's quite funny, tangential-like orbital character and then the energy contour. And the other tangential state that is not shown in this kx, ky plane is pz. But please remember that pz is another tangential state here. And these radial and tangential states are energetically split because of different quantum number, and therefore it has different quadratic splitting with respect to k. So there's one radial and two tangential states. The dispersion looks like this. So we will study this model more in detail for understanding orbital Hall effect in part 2. But now let's come back to the crucial role of the symmetry in orbital hybridization. So by orbital hybridization, we often actually mean as hoppings, basically. Interaction between two neighboring orbitals. For example, for p-orbital systems, PZ orbitals can interact via indirect overlap called pi hopping, pi bond, and also by direct overlap by sigma bond. And these two are examples of Slater-Coast parameter. And that is simply a systematic way to parameterize hopping parameters. One crucial aspect of this Slater-Coast parameter is that if there is a symmetry, for example, the mirror symmetry with respect to this plane, this px to pz hopping is forbidden. Do you see? And the reason is that we have a mirror plane here. So therefore, if you carry out the integral of this quantity, this vanishes because of plus and minus sign on the upper side and downside. So therefore, usually this hopping is forbidden in central symmetric systems. But what happens if we break the mirror symmetry? So imagine that there's another atom or this cute devil, could be another chemical or could be substrate or capping. Anyway, by electric field, imagine that you break the inverse symmetry in this way. And now what you see is that because the situation in the above and below the mirror plane are different, so therefore the hopping between two orbitals are now allowed. And this has very non-trivial consequence on the electronic states, and especially this interaction dequenches angular momentum and can generate finite angular momentum for electronic states. So for example, let's focus on the hopping from px to pz to the left and to the right. So px to pz hopping has two different terms. The first one is the hopping to the right. So there's hopping to the right, amplitude alpha times we attach the eigenvalue of the translation by plus a. A is the lattice constant. And then we have another contribution by minus alpha with the minus sign here, and then with the eigenvalue of the translation. Please remember that here the hopping parameters to the right and to the left have the opposite signs because of this shape of the px orbital, this plus on the right and a minus on the negative on the left. So we have anyway this sign k dependence times I for this matrix element. And if you calculate all 9 matrix elements for px, py, pz orbitals, what you can show is that there exists an interaction of this type of form when the inverted symmetry is broken along z direction. Okay, and this interaction, if you are used to spin physics, you will immediately notice that this is just Rajba interaction with L instead of spin S. And this is called orbital-Rajba interaction, and this can have result in finite angular momentum. For example, if orbital-Rajba interaction is very strong, and depending on the quantum number of m, you can have clockwise, no, and counterclockwise angular momentum texture in the momentum space. This is, for example, can happen in p orbital systems. But in reality, in 2D, there can be strong anisotropy between pxy and pz orbitals. So therefore, the textures do not exactly have these clockwise, non-counterclockwise shapes. So let's look at an example. One example that is so, in my opinion, important as a textbook example is bismuth silver surface alloy. And the system looks like this in a way that bismuth atoms are mixed together with silver on a surface in a supercell structure by square root 3 times square root 3. And because silver atoms are smaller than bismuth atoms, so bismuth atoms are a bit corrugated from the surface. And this corrugation has very strong impact on the symmetry breaking and leading to orbital hybridizations, breaking the mirror symmetry. So when you analyze the orbital angular momentum of p plus 1, p0, and p minus 1 bands, as shown here, and even without spin-orbit coupling on this blue dashed line, this shows that very clear clockwise, zero, and counterclockwise texture of angular momentum around the gamma point. So this is, I think, quite textbook-like example of the band structure and the orbital texture. Another important example, which I think more important from recent experiments is that uh, when copper film is oxidized from the surface, this oxygen can have significant influence on breaking the inverter symmetry. And the inverter symmetry breaking in this case is more chemical. So it's not only just physical, I mean, just potential effect. Let me explain you this. So, imagine that there is no oxygen, then d orbitals of copper atoms, let's say from Cx to Xy, is forbidden in the same manner as I explained you before for p orbital systems. But because can be p orbital, if there is an oxygen, then Zx orbital can go to px orbital of the oxygen, and it can go to then xy orbital of the copper. And this process can also result in the Rajma interaction, and this can result in very pronounced interfacial state between oxygen and copper layer with very strong orbital angular momentum value and has very clear this circular orbital texture at the Fermi surface. So orbital Rajma interaction, in fact, can offer a very nice way to generate angular momentum at the surface. And but for details, I'm going to also explain you more in the part two. So in part one, we have looked at how the orbital information is encoded in the block state in a way that block functions are constructed from atomic orbitals, and then they can serve as basis states. And this C is called character of the band, orbital character, and this C can change in K space, and this is called orbital texture. And orbital texture appears in many different systems because orbit habitations are quite ubiquitous in many multi-orbital systems. And symmetry is so crucial because it decides what type of textures are allowed. And for example, when the inverter symmetry is broken like this, by corrugated structure of oxygen on top of copper, you can have very strong orbital texture. So that's it for the first part. And I hope this was useful. And I want to see you also in the second and third part. Yeah, thanks a lot and bye.